Hello, myself Dr. D.K.Shedge, Professor in Electronics and Telecommunication Department, AISSMS Institute of Information Technology, Pune. Today we are going to discuss with integrator using operational amplifier. Circuit in which output voltage is the time integral of the input voltage is called integrator, or this also will be called as the integrating amplifier as it is using the operational amplifier. The circuit consists of a capacitor in feedback and a resistor in series, and then using virtual ground concept we can write very easily the equation at inverting input terminal. The current entering equal to current leaving. The current entering will be current flowing through resistor. Leaving will be current flowing through capacitor. The simple equation can be written for that current V in minus 0 divided by R into C d by dt of 0 minus V0, that is the current flowing through capacitor. Then we'll get equation for dV0 as a minus of 1 upon RC V in dt. Integrating that equation, we'll get expression for V0 as a minus of 1 upon RC integration of V in dt. Here we neglected the constant of integration. Actually, constant of integration will be the output offset voltage, which is quite low or which can be taken care of. If such integrating amplifier is applied with a sine wave, then we know with the help of that equation we'll get that output will be the inverted cosine wave. Here we'll get output as a cosine wave. If such integrating amplifier is applied with a square wave, then using the equation of integration we know the integration of constant will be t, thus we'll get a triangular wave as output with the input of a square wave. The frequency response of such ideal integrator, this is called ideal integrator. Such ideal integrator can be written very easily by writing the gain of this non-inverting configuration, A equal to impedance of in a feedback divided by impedance in series. Now in feedback there is a capacitor, in series there is a resistance. That's why minus jXc upon R will be the gain of amplifier, which will be given by 1 upon 2 pi FCR, where Xc is the reactance of capacitance given by 1 upon 2 pi Fc. So magnitude of such gain A, mod of A can be given by mod of 1 upon 2 pi F RC. This equation, from this equation if we plot that as a dB gain in dB versus frequency, then we'll get very easily that this plot will be falling at the rate of 20 dB per decade, and the frequency at which gain will become 0 dB, means magnitude of gain will become equal to 1. That frequency is denoted by FB. We'll get that frequency as 1 upon 2 pi RC. So gain then in terms of that frequency FB will be given by mod of A is equal to 1 upon F divided by FB. But here keep in mind that gain linearly falls from the initial value. Actually initial value will get whenever your impedance is having maximum value. But whenever impedance is having maximum value at zero frequency, impedance offered by capacitance can become infinity. It will become open circuit, or it will be just open loop gain of the operational amplifier at very low frequencies. There are drawbacks of such ideal integrator, that its bandwidth is very small and will be used for very small range of frequencies. Secondly, at low frequency just now discussed, the op amp will go into saturation due to open loop condition. So due to such limitations, ideal integrator need to be modified, and that is modified by adding one resistor in parallel with a capacitance in feedback. Then gain of such practical integrator, where one resistor is added in parallel with capacitor, can be found out. A is equal to RF in parallel with reactance of capacitance divided by R, actually minus of this. Then we'll get very easily the expression for gain. A is equal to minus of RF by R multiplied by 1 divided by 1 plus J 2 pi F RFC. Now we can define here one frequency at which the term, second term in the square bracket will become, its magnitude will become 1 divided by square root 2. That frequency will be called to be a corner frequency or break frequency, Fa, given by 1 upon 2 pi RFC. Then formula for gain now becomes A is equal to minus of Rf by R multiplied by 1 divided by 1 plus Jf upon Fa. This is nothing but the expression for the low pass filter. It shows the frequency response of low pass filter. And if such frequency response is plotted, we will get very easily that at lower frequencies, this is the expression for magnitude of that gain, mod of Rf divided by minus of Rf divided by R. So it will become Rf divided by R multiplied by 1 divided by square root of 1 plus F upon Fa square. At lower frequencies, at F very low value, this square bracket will become 1 and will get gain to be Rf divided by R. So at lower frequencies, gain will be following Rf divided by R in decibels. It will be 20 log of Rf divided by R. That will call as a DC gain. At very higher frequencies, the gain will be following the formula. Gain will be following the square bracket will become 1 divided by F upon Fa only. So gain will be linearly falling with the frequency. And at a frequency of Fa, we know at a frequency of Fa, the gain will be falling by 3 decibels. It will become 1 upon root 2 times Rf divided by R, that means falling by 3 decibels. And at a frequency of Fa, we know the gain will become equal to 1. So in decibels, it will become equal to 0. This is the actually frequency of integration, where the integrator will work as an integrator, that is the frequency from Fa to Fb. So Fb chosen to be quite larger as compared to Fa. Normally it is chosen to be equal to 10 times Fa. Fb is chosen equal to 10 times Fa. Thank you.